Recording? Yes, we are. All right. So to use the inverse function theorem, you need a function and you need the inverse function. So we're given this function g of x, and it's the, and let's see, f is its inverse. So what's the inverse of a cube root? What's that?
Inverse.
Inverse.
No.
Ruh-roh. What's the inverse of a square root?
1 over 2. Nope. Okay.
What's the opposite of taking a square root? A square. So what's the opposite of taking a cube root?
Cube.
A cube. Oh my God. All right. It's only Monday, right? Oh no, it's Tuesday. Darn it. All right. So g inverse of x, which we're also going to call f of x, is x cubed. All right. So first step is we got to find the inverse. The first one was a lot harder than the second one. So to find our g prime, we need to know the derivative of its inverse. Okay? So what's the derivative of x cubed?
3x squared.
3x squared. So we got that. So this was step 1, by the way, right here. Step 2 is to take the derivative of that function. Step 3 is to plug g into it. So we want to know what happens if we replace that x with g of x. What's g of x here?
X. Cube root of x.
Cube root of x. Yeah, so that's step 2. Now we can clean this up a little bit. What's another way to write cube root? X to the 1/3, right? So this is going to give me 3x to the 1/3 squared. Power to a power? Multiply them. So 1/3 times 2 is 2/3. So I get that this is 3 times x to the power 2/3. And then the last step is to flip it. So step 4, 1 over 3x to the 2/3. That should be the derivative of my original function. So I'm just going to go back and plug some of that stuff in, and there's one more question to answer about this. So what is the inverse function if the original function is the cube root? Well, that would just be x raised to the 3rd. What is the derivative of that new function? That would be 3x squared. What happens if you substitute the original function back in there? Well, we got 3x raised to the power parentheses 2/3. And then the last step is to just flip it. So this is just a procedure for running through that inverse function theorem. So then I'm just going to get 1 over parentheses 3x raised to the 2/3. And that supposedly is the derivative. So down here it says, hey, use the power rule on x to the 1/3 to see if you get the same thing. So let's double check, see what we get. New page. So the derivative with respect to x of x to the power 1/3 is 1/3, there we go, times, let's see, 1/3 minus 1. 1/3 minus 1. 1/3 minus 3/3, which is negative 2/3. So 1/3 x to the negative 2/3. What could the negative tell us to do?
Flip it.
Flip it. Yeah, that's a fine answer, by the way. I love that. You could circle that on the test and say, here's my derivative. But we could take it a little farther and say that's 1/3 times 1 over x to the 2/3. And multiplying fractions, you just multiply numerators, multiply denominators. Do we have a match here?
Mm-hmm.
Yeah, so same thing, different technique. And with any complicated problem, there's going to be more than one way to do it. So,
stupid question. So, the inverse, right? Don't you substitute, change x for y and solve for y?
to calculate the inverse, that's, yeah, if you don't recognize it immediately, you have to switch them and solve. Yeah, are you on number 1?
Yeah, I couldn't.
That's okay, let's take a look at number 1 then. All right, so I got an answer. Type it in any way you want. The computer's pretty forgiving on this one, I believe. So I could call it 1/3 times x raised to the power negative 2/3 if I want, or I could type it exactly the same way I did above. I think it'll say, yeah, good job. Oh, which one didn't it like? Oh, it didn't like that one.
Your syntax is wrong. You have to put parentheses.
Oh, I'm missing parentheses there.
What?
Darn it. Oh. Flipping. Okay. I don't know why I zoomed in that much. That was a little crazy. All right, let's try number 1. So number 1 gives us the function x plus 4 over x. First step is the hardest one, find the inverse function. So let's put that in the notebook. All right, procedure for finding the inverse function is twofold. First, we need it as y equals x plus 4 over x. And then you solve for x and then switch them, or switch them and solve for y. So I'm going to solve for x here. So to do that, I guess I would multiply this x to the other side. So I get xy equals x plus 4. Let's see, I'm solving for x, so I need to collect the x's on one side. So I'm going to subtract that x over. Oops, equals 4, sorry. Now there's too many x's here. Agreed?
Mm-hmm.
What can I do? Factor.
Oh.
You know, so if I pull an x out, I'm going to get a y minus 1 as the other factor. And so now I can just divide by that. 4 over y minus 1. And then switching them gives me the inverse. So g inverse of x is going to be 4 over x minus 1. Okay. Which I can also write as 4 times x minus 1 to the negative 1. Nice thing about the inverse function, it only has 1 x in it. The other one had 2 x's.
It's, shouldn't the bottom be 4 over y minus 1?
The last step is to switch x with y.
Oh,
Is the last step.
okay.
Yeah. I just did my switch there. And this was an x right here. So that's the inverse function in either form. And then the next step is going to be take the derivative of that. But the hardest part was getting that function, without a doubt. So 4 over parentheses x minus 1. There's one version of it. The derivative of that. So this version requires the quotient rule. This version requires the power and chain rule. Which one do you want to do? Oh, wow, we got quite a mix in the room. Do it your own way and tell me what you get. How about that? You decide. Either use the quotient rule or use the power and chain rule. I'll try it both ways. So either way, I get negative 4 over the quantity x minus 1 squared. Remember with the quotient rule, the derivative of the numerator is 0. Comes up nice. Derivative of the denominator is 1. Here, the 4 with the power and chain rule, the 4 is just a constant that just hangs out in front as a multiple. And the power rule says the derivative of something to the negative 1 is negative 1 times that thing to the power negative 2. Multiplied by the derivative of the inside, which is 1. And clean it up. All right, so we have that derivative. So that's the second step in the inverse function theorem, which again says if you want to have some inverse function, and you want to take its derivative, then take 1 over the inverse of the inverse prime with the inverse function plugged in. So we found the inverse of the function, we took its derivative, now we just need to plug the original function back in. So let's see, we're on step 3 of this. So our derivative is -4 over parentheses minus 1 squared. What was the original function? Anybody remember?
X plus 4 over X.
X plus 4 over X gets substituted in here. A note on X plus 4 over X, you could rewrite that as X over X plus 4 over X, which should be 1 plus 4 over X. And why is that a handy way to rewrite it? Because what are we doing to it next? We're subtracting 1. That's kind of nice. So then this is going to become -4 over 4 over X squared.
Oh no, I dropped the
And that cleans up kind of nice. So let's see, we're going to have a -4 over a 16. And then if I have divide by X in the bottom, that's going to become a multiply in the top. So that's going to be -4 over 16 times X squared, or -1/4 X squared. The next step. So we found the other function, we took its derivative, we substituted in. The last step is to flip it. So if we flip that over, what are we going to get? Oops, wrong button. I think we're going to get -4 over X squared. Is that right?
Yeah.
Flip. Step 4. -4 over X squared should be the last step there. So that should be the derivative of the function I started with, which was g of x equals x plus 4 over x. So this should be g prime of x. And then the last step says check it using the quotient rule. See if that worked out. So the inverse function theorem is just a technique for finding derivatives. You could break it down into a 4-step process if you want, or you could just, if I don't ask you to do the 4-step process, just try and use that idea to come up with an answer, which I think is probably what number 6 is going to look like. So let's take a peek. So that was number 1. We did number 2. We're leaving this one. Yeah, cosine inverse of 6t to the 5th. Let's give it a try. And actually, we don't even need to use the inverse function theorem on this one, because we already established the derivative of the inverse cosine, true? In the last class. So we don't need to do it again. Unless you really like that kind of thing. So my preference is to write this as an arc function. So here I'm going to say this is the arc cosine of 6t to the 5th. And the other day we established that the derivative with respect to, I'm going to use an x here, of the arc cosine of x is, anybody got that?
Oh. Nope. We didn't do our cosine.
We didn't do our cosine.
No, we only did
sure?
arc sine and arc tan.
Oh my.
Because you said we were going to do it today, we were going to do the rest of the arc trig functions.
Okay. So here they are. Okay, so what do you need to know? You should know the arc sine, the arc cosine, and the arc tangent. The other ones aren't a big deal. How is it related to the arc sine?
It's the negative.
Negative. And remember before I talked about most co-functions end up having a negative in the derivative? This fits that pattern yet again. So it's just the opposite of the derivative of the arc sine, which is kind of nice. So you need to know those first three. I would recommend memorizing those. Otherwise, you have to prove them each time, and that's kind of some hairy trigonometry.
Same thing with negative. Okay.
The arcsecant and arc cosecant are kind of wild because they have an absolute value of x in the denominator. Makes them a wee bit more complicated.
Is that 1 plus x squared for tangent, right?
Tangent is 1 over 1 plus x squared, correct? So those are the main three you need to worry about. If we ever need the other ones, we'll look them up.
Are we gonna need them on the test?
Nope. All right, so here, the derivative is just 1 over, or negative 1 over the square root of 1 minus x squared. And if we were to replace the x with a u and think about the chain rule, then the only difference is we get a u prime in the top there. Chain rule just says multiply by the derivative of whatever was inside. So can we do this function f then?
Yes.
Yeah. No, we're going to do it with t's instead, right? So we're going to have the derivative with respect to t of the arc cosine of 6t to the 5th power. So that's going to be a negative 1 over the square root of 1 minus whatever u is squared. And u in this case is 6t to the 5th. And then I have to take the derivative of that and slap it in the top. What's the derivative of 6t to the 5th?
30t to the 4th.
30t to the 4th, yeah. And we can clean this up just a little bit, but not very much. The denominator, I can carry out that square, use a slightly less ink, and multiply the negative 1 by the 30. So I could say this is negative 30 t to the 4th power over 1 minus 36t to the
6th.
10th.
Oh.
That's a 5.
Oh, it's a 5. Okay,
Yeah,
sorry. Also, isn't that all square rooted?
And that's all in square root, yep. And that's about all we can do with this. Nothing cancels. Don't try. Bad things will happen. All right, we're going to do a little bit more with inverse functions tomorrow, and I recorded a video for that already. It's in the playlist. So the playlist will be a little out of order for those of you who look at it. It's going to have day 22 before day 21 because I recorded that before this class today. So next we're going to play with section 3.8, implicit differentiation. It is, it's pretty cool. All right, so implicit differentiation. And it's actually a pretty simple idea. Implicit differentiation allows us to take derivatives of whole equations instead of just a single function. So that's one big idea. And you'll see what I mean in a sec. And the other big idea here is anytime we see a y, we assume it is some function of x. Is an assumption we make. All right, so consider the equation x squared plus y squared is equal to 1. Does that look familiar?
Yes.
Yeah, that's the unit circle. Okay. we are going to find, eventually we're going to find a tangent line to this. So tangent at the point, which point was I thinking? I was thinking of 0.8 comma 0.6.
Interesting.
Is a point on that. So one way to do this would be to take this, solve for y, take the square root of each side, but we get it with plus or minus the square root, and we got to figure out whether we want the plus or the minus. What implicit differentiation allows you to do is just say, let's just take the derivative of the left side, and then take the derivative of the right side. So I'm just going to take the derivative with respect to x of x squared plus y squared, and set it equal to the derivative of the other side. Now, you've done stuff like this before, right? You square both sides of an equation. You divide both sides of an equation by 2. You take the square root of both sides of an equation. You've taken logarithms of both sides of equations. Derivative is kind of a function. You can take the derivative of both sides of the equation. As long as the derivatives exist, this is okay. But there's a problem. What variable am I taking the derivative with respect to?
X.
But what do I have over there?
Y.
However, what do we know about y?
They equal each other.
It's a function of x, so the chain rule applies.
Yay.
Yeah, so it's just an application of the chain rule. Okay? So let's just do that on a new page. Move this up here. So help me out. Oops, that is not a pen. Yeah.
Oh, back page.
That wrong
Are you back on
page.
pages? One more page.
No, we should.
That's one.
Okay, I got it.
Okay. So I think I have a pen now. Yes. So the derivative with respect to x of x squared plus y squared. And then on the other side, derivative with respect to x of 1. So left side, we have a rule that says we can break a derivative over a sum. So that's nice. We can take the derivative of x squared separate from y squared. What's the derivative of x squared?
2x.
2x. Plus the derivative of y squared. At first glance, it is 2y, but the chain rule says, hey, but y is a function. So you got to multiply by its derivative,
X.
y prime.
Yeah.
That's all the chain rule says there. That's why as some function of x, chain rule says you got to multiply by its derivative next. Chain them along.
Isn't y prime 2y?
What's that? You okay?
Yeah.
Yeah, so I took the derivative of y squared. Chain rule says multiply by the derivative of the inner function, which is y. Y is the inner function here.
Oh, okay, I see. So
Isn't y prime also dy dx?
We could call it dy dx, correct. Yeah. What's the derivative of 1?
0.
0, lovely. Next thing, we try to solve for y prime if possible. Because y prime is our slope function, it's going to help us find the tangent. And there's only one y prime, so that's not too bad. What should we do first? Subtract the 2x. Yep, so we're going to get a 2y, y prime equals negative 2x, and then divide by 2y. So y prime is just negative 2x over 2y, which I could also write as the opposite of x over y. Right, those 2's divide out.
Hey, didn't we talk about this?
Cool. This came up before when we were doing some other playing around. I think it was, what was that with? I can't remember, but yeah. Little geometry of the unit circle. So now this y prime is a slope function, right? Do I know the point I want to be tangent at?
Yes.
Yeah, that's the point 0.8 comma 0.6. That's x, that's y. So the slope here, what's up?
The tangent point that's on the other side.
Yes, we will see that. Yeah. So I want the opposite of x over y. So opposite of 8/10 over 6/10, which cleans up quite a bit. Let's see, 8 over 6 is really what, 4/3? So the slope is negative 4/3. Let's ask Desmos if this looks good. Which means implicit differentiation works in at least this case if it looks good. So Desmos, x squared plus y squared equals 1. And there's that beautiful circle. Zoom in on it. We are curious about the point 0.8, comma 0.6. Hey, it does lie on the curve. I got lucky. And then the tangent line, I'm just going to use my point slope form of a line. So that would be y minus 0.6 equals 4/3, negative 4/3 times x minus 0.8. Bang! We nailed it. Woo!
Okay, I have a question.
Yes.
How did you get negative 4/3 from 0.8 over 0.6?
Good question. So since these are both tenths, 8/10 and 6/10, I was thinking divide the tenths out, which leaves me 8/6.
Okay. Okay.
Yeah, sorry about that.
I just
Kind of
moved
buzzed
from
through yours
decimals
and
to
check.
whole numbers and freaked me out a little bit. But
Yeah.
You noticed that.
Yeah, you could think multiply top and bottom by 10, that gives you 8/6, and then divide both sides by top and bottom by 2.
Yeah.
Okay. Cool. So implicit differentiation is a powerful tool because we didn't have to solve for y, which would have been a fair amount of work, another page, right, or half a page or something. So it allows us to do some powerful things. Now, there are equations that aren't solvable. Okay, so, or at least they're wicked hard to solve and it would take more time than we have. So consider the equation x cubed plus y cubed equals 6xy. Cubic equations are pretty darn hard to solve. Anybody remember memorizing the cubic formula? No, you never memorized the cubic formula. It's nasty. It makes the quadratic formula look like add in 2 plus 2 perhaps, right? So solving this for y is non-trivial, okay? It didn't come up in any algebra class you've done, I bet. What does this look like though? Let's graph it. Could it be a circle? Could it be something else? Let's see, Desmos. Not a circle.
Probably like a
X raised to the third plus y raised to the third equals 6xy. Ooh, it's a loop-de-doop. Yeah, like a roller coaster. This is called a folium. In particular, a folium of Descartes. Descartes was this old philosopher, math guy from several hundred years ago.
What does the 6xy determine?
That determines the size of the loop and the asymptote, the slant asymptote here. So if I made that 6 something else like a 9 or a 1, you get a different size loop and you get a slightly different asymptote. Okay. All right, so I'm going to go with this one right here. And I even managed to find a point on here. So let me, oh yeah, besides 0, 0. Yeah, that was an easy one. I found that one. The point I found was 4/3, 8/3 is on this graph. So we're going to find a tangent to this sucker, tangent at 4/3, comma 8/3. But before we can do that, we got to take the derivative. And since we cannot easily solve for y, let's use implicit differentiation. Go for it. See what you get. Apply the same technique we applied to the circle. This one's a little bit more work because of the right side. You got to use the product rule along with the chain rule. You got to have the chain rule on both sides because every time we see a y, we think function of x. Chain rule. I need to reset my board while you guys work on that. That's strange slippage. So that's what the first go through should look like.
Is it 4/3 or 4/5 on tangent?
It's 4/3 and 8/3 is the point we're going to plug in eventually.
Okay, I'm a little lost on the back half of
The right side?
Yeah,
Okay. So the 6 is just hanging out as a multiple.
okay,
So then I take the derivative of x, which is 1,
right,
and the y just stays alone for a minute.
okay,
That's what the product rule says.
okay,
Then you take the 6 just hangs out, leave the x alone this time, and take the derivative of y, which is just y prime.
okay.
Okay, so that's a y prime there.
Wait, the white primes cancel.
They do not cancel, no. But you do have to collect them on the same side.
Sounds fun.
So now you gotta start moving stuff around. So for example, this 6y is gonna stay put, but I'm gonna bring this 3x squared over to the other side. This 3y squared y prime is gonna stay put, I'm gonna write it here. And I'm gonna have to subtract over the 6xy prime. And you feel free to do more than one step. I apologize for skipping a step there. But you should end up with that eventually. So I had to subtract the 3x to the right. And I had to subtract the 6xy prime to the left.
Why?
Why?
Yeah.
Because I want to find the slope, which means I need y prime.
Oh,
So it'd be nice if I could get the y prime alone.
okay.
Now, you could, at this point right here, you could just say, screw it, I'm just going to plug in x and y from the point. And then y prime will be the only thing left to solve for. That would work equally well. Does that make sense what I'm saying there?
Yeah.
More
Yeah.
fractions.
Yeah, so you have to trade variables for fractions. You know, take your risk. So on the left side, I'm going to factor out the y prime, which is going to leave behind, oops, I'm getting ahead of myself.
Can we factor out a 3y prime?
No.
Sure, we can factor out a 3y prime.
Well,
But you
Y
want
prime.
y prime by itself.
I do
so
want
why
y
would
prime
you-
by itself, yeah, so you could go either way.
Alright.
I'm just going to factor out y prime, and then I'll deal with the 3 later. So if I factor out y prime, I get 3y squared minus 6x,
Mhm.
which is kind of like the opposite of what's on the other side, which is kind of cute.
You divided it.
6y minus 3x squared. Yeah, so then we're just going to divide both sides by that parentheses, and that'll give us the derivative.
Yeah.
Oh.
So y prime is, let's see, 6y minus 3x squared over 3y squared
Minus the 6x.
minus 6x. Did I get that order right?
Yeah.
This is okay.
Where we plug in the.
So a notation that you're going to see in the homework sometimes is another name for y prime is dy dx. I want to evaluate that, that's what the bar means, at the point 4/3, 8/3. So that just means plug in that number there. So you'll see that notation in the homework. So then start slapping those numbers in. So I'm going to have a 6 times 8/3 minus 3.
Can we cancel out?
Oh, yeah, we should cancel some stuff out. Yeah, I'm way ahead of myself. Thank you, Carter. Who said that, Carter? Ben.
Carter, I take the credit.
Should we factor out a 3?
Yeah, we can factor a 3 from the top and the bottom, like you were saying before. And that simplifies to 2y minus x squared over y squared minus 3x. 2x, sorry. Let's see, is that what I got earlier? 2y. Uh-oh. Yes, that's what I got earlier. Yeah. All right, now plug in. So 2 times 8/3 minus 4/3 squared over 8/3 squared. Get that right?
Yep.
minus 2 times 4/3.
Is that 8/3 and 4/3?
Yeah, 8/3 and 4/3 for x, 8/3 for y. And then I did a bunch of fraction jiggery pokery, and I got this is 4/5.
Okay.
Do you wanna,
So do you want to see my fraction jiggery pokery?
Yeah.
Oh, fine, okay. So let's see, the next step here would be, that would be 16/3 minus 4 times 4 is 16/9 over 64/3 minus 8, nope, 64/9, sorry. Minus 8/3. And then what I would do next is multiply top and bottom by 9. That gets rid of all fractions within the fractions. 9 is the biggest, the common denominator.
But what if you just multiply by 3, then you wouldn't have, then you'd have a common.
Well, if I multiply by 9, then I'm gonna get, did I make a mistake somewhere?
No, never mind.
No,
I
it
was
is,
confused.
You see what I'm doing?
Yeah.
Multiply by 9. So if I multiply top and bottom by 9, stuff's gonna work out nice. Because it's gonna cancel all the denominators. So I'm gonna end up with 16 times 3 minus 16 over 64 minus 8 times 3. Which I think my next stage came out to, that's 32 over 40.
I would end up multiplying by 3.
Because the 9 is the 3.
Because 3 goes into 9 3 times,
Oh, okay,
right? And the same thing over here.
okay.
So then this becomes, I believe, 32 over 40. And then 8 goes into top and bottom, which gives us 4/5. Should be a slope there. All right, let's see if Desmos agrees. So the derivatives are a challenge here, and then once we have to evaluate, that's our next challenge on these problems. And there's going to be a few homeworks just like this. All right, so the point of interest, I believe, is, let's see, 4/3, 8/3, right? Yep, I got lucky, it lies on the curve, or pretty damn close. And then the equation should be y minus 8/3 equals 4/5 times x minus 4/3. Ooh, that looks good. Nice. Isn't that exciting when a plan comes together like that? Woo!
That's gorgeous, Gary.
Isn't it? Yeah. You know, it'd be even more fun is to set up a variable for the x value, and then we could drag the point around and watch the tangent line change. It's like almost like a video game. Kyler's like, I don't think so. All right. Ooh, I have my parenthesis in the wrong spot. I hate that. Oh well, Desmond's fixed it for me. How sweet of him. Only my open math would do that for us. All right, let's take a look at a homework problem in my open math, and then we'll call it quits for the day. That's the wrong section. Create implicit differentiation. Let's see what lucky number 7 looks like. Ooh, oh crap, that's not supposed to be in this section. Darn it, I thought I cleaned all the E's out till next section.
Obviously.
All right, well, we're gonna do E right now then. It's E is wicked easy. It's one of the few functions who is its own derivative.
It's e to the x.
Derivative of E to the x is E to the x.
Yes, yeah.
Yeah, so it's pretty easy.
easy.
E, Z, it wasn't, that's
Wait,
funny.
is that actually why it's just called the natural curve though? Or-
No, that's a different reason it gets that name. So
Will we cover that in this class or no?
why it's called natural?
Yeah.
It's not really a very interesting story.
Okay. Fun.
All right, so thing you need to know to do this problem is that the derivative, ooh, whoa.
What did you do?
I don't know, my electromagnetic field is a little spooky there. Dx of e to the u, assuming u is a function of x, the derivative of e to the anything is e to the anything.
I like
And then the chain rule says multiply by whatever the power was, its derivative, is times u prime. E is lovely. I justified
Do we need to
it.
remember that
into
now, or can we forget that until you bring it up again?
You can remember it now. Yeah.
So
I
it's
go over a little
the
more
same.
detail about why this is true in the video for tomorrow. So we're just going to apply it. So we're just going to do implicit differentiation here. So the derivative with respect to x of e to the 3xy versus the derivative with respect to x of y to the fourth.
Versus.
You said,
That's
you
versus
said
the, instead of
d
equals.
of x, e
Equals
to the
versus-
3x
Yeah,
versus.
All right, yes. Yeah. Well, they are competing against each other, right? Versus tag team. All right. The derivative of e to the something is e to the something. Then we have to multiply by the derivative of that something, and here we have to use the product rule. So the 3 just chills out. Derivative of x is 1, and then the y chills out. Then we have to add on, the 3 is still hanging. X gets to chill out, we need the derivative of y,
Y prime.
which we usually call y prime. And if you accidentally mistake that to y to the first power ever, then you probably want to use the dy dx notation instead. But hopefully you're getting used to that prime as a power, not a first power. Sorry, a derivative, not a first power. Other side, what do we got?
4y to the third y prime.
Yeah, times y prime. Sweet. Okay, let's see. Usually we want to solve for y prime. What did they ask us to do here? Oh, that's not it. Cancel. Find y prime, dy dx. Yep. So we had a little bit of algebra to do here.
You got a minute.
So the question is, do we distribute the e to the 3xy or do we divide it to the other side?
Divide it to the other side.
Okay. So 3y plus 3xy prime is equal to 4y cubed y prime over e to the 3xy.
Oh, wait.
That's what we chose to do.
Now you're gonna divide by the other number.
Oh, you thought, well, dividing by the other number wouldn't help because then I wouldn't recommend doing it the other way.
Wait,
Sorry.
I just really didn't want to multiply that through.
So you wanted to divide by the parentheses, right?
Yeah.
Although that gives us all the y primes on one side, one's in the top, one's in the bottom, and we're kind of screwed.
Yeah.
So this is a better alternative. Otherwise, you have to distribute.
Would you rather distribute or divide?
You could factor out a 3, but that's not going to really do much good at this point. Yeah. So what I would do next is I would take this term, subtract it over to the left. Then I have all the y primes on the same side. Okay. So then I have, I think, 3y equals that crazy thing, 4x cubed y prime over e to the 3xy minus, what am I subtracting here? 3xy prime. 3xy prime. Now we can pull the y prime out on the left side.
Oh dear.
And that leaves me 4y cubed over e to the 3xy minus 3x.
Do we have to divide by that?
Then we have to divide by that. So that's going to give me 3y over that crazy parentheses, 4y cubed over e to the 3xy minus 3x. And that is one of many versions of y prime. If the fraction within a fraction is freaking you out, get over it.
Oh,
It's all right.
I got 3y e to the 3xy divided by 4y thirds minus 3x
E to the 3xy.
e to 3xy.
Yeah, so that would be an alternative to this.
I do the fraction.
If you had distributed here in the first place, that would be a lot like in this, from page,
Oh, you ran out of time.
I'm out of time. That would be a lot like multiplying top and bottom by 3xy. So the alternative William mentioned was, another answer would be 3y e to the 3xy over 4y cubed minus 3x e to the 3xy.
If it doesn't give us a point, do we just put in the,
It just wants the derivative with variables in it.
okay.
That's the other option.
That second one looks more manageable.
The blue one,
Yeah,
so that would have happened if we distributed first instead of dividing.
I think we like that maybe.
All right, you guys have a good night, and make sure you check out the video I posted tomorrow. Feel free to come meet here and do math together. The room will be available to you if you want. Otherwise, I will see you guys on Thursday, which is a review day for the test on Friday.
We haven't, is this 3.9?
This is 3.8. 3.9 is derivatives of logs and exponential functions.
Is that on the
It's
test?
actually not that bad.
Did you just say the test is this week?
The test is Friday.
So.
That's why I posted the sample exam last week.
But are we gonna get to
Okay.
3.9 before
So
the test?
I'm screwed.
3.9 is tomorrow.
Oh, okay.
That's what the video I made. I
Okay,
reposted
I
is for.
thought you said 3.8.
This is 3.8. There's already a video waiting for you for 3.9.
Did you learn?
Yes.
Piece of paper.
Yes. Hang on, let me stop this.